In the darkest reaches of the cosmos, there's a region so empty it looks like a mistake in the universe's design. Tonight's journey drifts through the Boötes void, a vast hollow surrounded by delicate walls of matter, faint gradients and slow-moving structure that should not feel this clean. If that sounds impossible, stay close. The story is calmer and stranger than it seems. And if this kind of deep space sleep documentary helps you unwind, please tap like, subscribe and turn on notifications. It quietly tells the algorithm to bring more nights like this. A vast emptiness can seem ordinary until its edge becomes too crisp. In the Boötes void, the hollow looks wide enough to be routine, yet the boundary arrives with unusual sharpness. Around it, the cosmic web gathers into pale walls. It stretches into thin strands. Inside, darkness opens as a long, quiet basin. The basin spans about 300 million light-years across, and its rim seems narrower than a slow taper suggests. A slow view rests on the boundary where faint galaxies thicken abruptly. Their spacing tightens over a relatively thin band. Then the count drops away, and the interior becomes sparse again. Cosmic web is the filamentary pattern of matter on large scales. It resembles a network of river channels seen from far above. It resembles roots in soil with open pockets between them. It matters because voids are carved out of this pattern, not placed beside it. Along the strands, gravity gathers matter into knots. Between the strands, gravity has less to gather. Over long spans, the thin places lose more material to the denser ones. In most regions, the loss leaves a gentle gradient. A typical void shows a broad glide from wall to centre. Here the glide looks steeper. The boundary suggests a stronger contrast between rim and interior. 300 million light-years is also a travel time. Light crosses that span in 300 million years. That duration feels like weather repeating through countless seasons, yet remaining slow by cosmic standards. In ordinary regions, such a path crosses many weak layers of gas. It crosses small groups and faint filaments. Each layer adds a slight scatter. Each group adds a slight bend. Inside this hollow, those layers appear reduced. The darkness is not perfect. It is simply emptier than the surroundings in a sustained way. A long corridor of space forms where starlight meets fewer obstacles. Even that clarity can create an illusion. When the background is quieter, the rim looks sharper by contrast. So the attention turns from brightness to shape. The rim is not only dense, it also looks thin along the line of sight, like a shell rather than a wide slope. Gravitational lensing is light bending slightly under mass. It is like distant scenery seen through uneven air. It is like a pattern under clear water warped by ripples above it. It matters because mass can be traced even when it does not shine. In a simple void, lensing is weak and smooth. The bending changes slowly across wide angles. The rim behaves like a shallow bowl, not a sharp ridge. Here the rim becomes a quiet test. If the bending strengthens abruptly at the boundary, then hidden mass concentrates more than expected. That does not require a bright object. It requires a gradient in what pulls on light. A slow image forms of background galaxies stretched into tiny arcs near the edge. The arcs are subtle. They gather in the same band where the visible wall thickens. That alignment clarifies one point. A narrow rim is not only a pattern of lights, it can also be a pattern of gravity. Another detail follows from how hollows grow. Material drains from the interior and collects near nearby filaments. The edge can become a ridge, a band where galaxy counts rise. In many voids, the band is broad. Here it seems tighter, like a layered shell. A limit of observation arrives naturally in a place defined by absence. The interior is measured by what fails to appear. A faint galaxy can fade below visibility because its light spreads thin. A small group can hide because depth collapses into a single projection. Two distant structures can overlap and mimic a wall. Distance estimates also carry blur. In a region this large, a modest uncertainty becomes millions of light-years of shift. The centre then becomes the least reliable part to interpret. The edge remains more stable because it is defined by change rather than by nothing. Another slow view rests inside the hollow. Only a few isolated smudges appear, separated by wide spans of dark. They do not form a rich lattice. They do not fill the space evenly. The emptiness becomes tangible through spacing alone. From that spacing comes a firmer constraint. A void this wide cannot be carved quickly. Gravity and expansion work over immense spans, and matter needs time to flow. So the size implies a long history of drainage. If the void is too large, either the starting region is unusually empty, or the drainage is unusually effective. Both options are rare in the usual pattern of the web. The rarity is the reason the void matters. It tests whether the largest scales behave predictably. The outline adds one more constraint. Large hollows tend toward roundness as many directions average out. An elongated outline implies a preference. The basin grows more along one axis than another. That preference can arise if one side is reinforced by a thicker wall, another side can be bounded by thinner filaments. The void then stretches as matter drains more easily in one direction. Scale also matters. A single galaxy holds its own stars and dark mass. A cluster holds many galaxies together. The cosmic web holds both walls and cavities. This hollow sits on that larger scale, so a thin edge becomes a clue about the largest flows. A wide view traces the rim like an oval ring. The ring is not uniform. One side looks slightly sharper. The opposite side looks more diffuse. The difference is gentle. It still hints at a gradient that is not perfectly balanced. The calm promise settles without sharp suspense. The next step is to watch how ordinary voids form from the cosmic web. The next step is to see why most boundaries remain soft instead of thin. With that baseline, any feature that should not be there becomes clearer by contrast. The darkness remains wide. The rim remains delicate. The scene eases toward the rules that usually carve emptiness and toward the first places where those rules begin to strain. Emptiness grows in space the way hollows form in a field of drifting sand. In that region, a void forms through slow outflow from slightly thinner places toward slightly thicker ones. The first clue is subtle. A faint imbalance appears early. A patch begins with less material than its neighbours. Gravity then deepens the difference. The denser outskirts pull more strongly. The thinner interior pulls less. Over long time, the interior becomes a gentle basin. The rim becomes a faint ridge. A slow scene settles on a wide sheet of dim matter. It shows a shallow depression. The depression is surrounded by brighter strands. The strands look like soft cords under tension. Along those cords, small clumps appear as knots. Between them, the basin stays quiet. Density contrast is difference in matter between a region and its surroundings. Like wind over sand, a small dip can become a larger hollow. Like a thin spot in a fog bank, a gap can widen as the fog drifts away. It matters because voids do not need special causes to begin. They need time and a small imbalance. A small payoff arrives with that idea. A void is not carved by removal. It is shaped by redistribution. Material does not vanish. It slides outward and stacks gently along the edges. In a typical void, that stacking is spread out. The rim is broad. The interior fades gradually toward its centre. That gradual fade is expected because many directions average out. Flow comes from many angles. No single wall dominates the draining. At this distance, the visual anchor returns to the rim. The rim is not a hard border. It is a zone. It is a region where spacing between galaxies tightens slowly. A thin layer of gas can also gather there. The gas is rare. It still forms a gradient. A faint haze can become slightly denser near the wall. The haze then thins again toward the basin. The basin is not empty of everything. It is empty of the usual richness. A second payoff rests inside that detail. A rim is a record of how the interior empties. A thick rim suggests long drainage. A thin rim suggests either sharper flow or sharper beginnings. Time becomes the quiet driver. A void grows over spans measured in billions of years. About 1 billion years is a useful scale here, like a slow cycle of erosion that turns sharp edges into soft slopes. In that span, weak pulls still matter. They act without pause. They act across immense distances. They move material by tiny accelerations that add up. The basin widens. The rim shifts outward. The chords of the cosmic web stretch slightly. The knots become more pronounced. A slow image holds on a filament near the void. The filament is not straight. It curves gently. Along it clumps appear at uneven intervals. Between clumps the filament narrows. The narrowing is physical. The material is not uniform. It forms a tube with a denser core. Around the core a fainter sheath spreads out. The sheath fades into the surrounding darkness. That layered structure explains another point. Voids are shaped by what surrounds them. A thick filament wall can act like a bank. A thinner wall can leak. So a void can grow more in one direction than another. The basin then becomes oval instead of round. Its rim becomes sharper where banks are stronger. Its rim becomes softer where banks are weak. Another small payoff lands here. Shape is not decoration. Shape is a clue to the directions of long flow. Expansion adds a gentle complication. Space itself stretches. That stretch carries filaments apart. It also makes all distances grow. Yet the stretching does not erase contrast. Dense regions still slow their own expansion through gravity. Thin regions expand a little faster. That speed difference is slight. It still accumulates. A void becomes a place where the stretching wins more often. The interior therefore dilutes more quickly. The rim therefore collects more relative to the centre. A slow scene turns inward again, turns. The interior looks like a dark lake with a smooth surface. Across it faint wisps drift like barely visible smoke. The wisps are not random. They align with the large-scale flow. They form faint streaks that point toward the rim. Those streaks are gradients in the thinnest material. They are more like a whisper than a river. They still reveal direction. The ridge at the edge is not a wall of light. It is a compression of spacing. Galaxies become closer together there. The change can be measured by counts. It can also be measured by motion. A limit of observation enters softly at this checkpoint. Distance in deep space is inferred, not touched. Motions along the line of sight can blur structure. A group drifting slightly can appear stretched. A rim can appear thinner than it is. A basin can appear deeper if the far side is shifted outward in distance estimates. Sparse traces also mislead. If only a few galaxies outline the interior, randomness can mimic a smooth cavity. If a faint filament hides below visibility, the basin can look cleaner than it is. The limit is not the sky itself. The limit is how three-dimensional shape is reconstructed from faint signals. That limit matters because a sharp rim can be real or apparent. The difference must be teased from patterns that repeat across many directions. Another payoff settles with that caution. The safest features are the ones that persist under many reconstructions. A rim that remains narrow under different distance treatments is more convincing. A basin that remains sparse across different traces is more convincing. With that in mind, typical void growth returns to a simple expectation. Broad voids should have broad transitions. They should not look like cavities cut by a single stroke. They should look like basins worn by many gentle currents. So when a void appears unusually large, and its rim appears unusually thin, the ordinary story begins to strain. It does not break yet. It begins to demand better measurements of shape and flow. A final slow image rests on the void's edge as a layered band. The outer side shows a thicker weave of filaments. The inner side drops away quickly into darkness. The band looks like a raised lip around a shallow crater of night. The next step is to treat distance itself as a tool of calm inference. The next step is to let light act as a timeline through the hollow, and to see what absence does to what arrives. A void is not only a place in space, it is also a place in time. At this distance, the Boötes void is seen as it is long ago, and that timing shapes what the darkness seems to contain. Light behaves as a traveller that carries its departure date within its arrival. When a faint galaxy is seen near the void's far side, its light begins the journey earlier than light from the near side. That simple offset becomes an anchor. A wide hollow is not inspected all at once. It is inspected as a layered sequence of moments. A slow scene forms as a long dim stream of starlight crosses the void. The stream passes through a clear interior. It then reaches the rim where the stream becomes slightly mottled. The mottling is not noise. It is a record of passing through denser surroundings. The rim looks like a thin veil with a sharper texture. The interior looks like open air. That contrast unlocks a quiet rule. Emptiness is defined by difference, not by absolute black. Redshift is light stretched longer by cosmic expansion. Like a rubber band eased wider, its markings drift apart. Like ripples spread on a widening pond, peaks move farther between them. It matters because stretch turns distance into a readable ordering of time. As light travels, its waves lengthen. The same source arrives with a gentler, lower frequency. The change is small in a nearby region. The change grows in a far one. So a broad view can sort structures by how stretched their light becomes. The void then gains depth. The near rim and far rim separate into layers. The interior becomes a corridor with thickness. In that corridor, absence can be tested. If a filament lies inside, it tends to show up at a consistent layer. If only the rim appears, then the interior remains thin in content across layers. A slow visual returns to the boundary. The wall of galaxies is not a solid fence. It is a band with knots and gaps. Its thickness can be compared across layers of time. When the same band stays narrow through multiple layers, the sharp edge feels more real. That resolves one question. A sharp boundary is less likely to be a single projection if it repeats across depth. The scale shift remains gentle. A single galaxy is a small island of light. A void spans a volume large enough to hold many thousands of such islands. Yet the evidence arrives as faint points. Each point is a message from a particular moment. The mind prefers to treat the scene as a photograph. The scene is closer to a slow scan through time. That is where intuition begins to strain. The interior can look quieter simply because distant faint objects are harder to see. A faint group can slip below visibility and make the basin seem cleaner. A delicate filament can fade until it is indistinguishable from the background. The limit is not only brightness, the limit is also depth uncertainty. If distance is inferred with blur, then a thin wall can smear. A broad slope can masquerade as a thin ridge. A hollow can deepen in appearance when uncertain layers pile into one another. Another small payoff settles here. The emptiest region is also the easiest place for absence to be exaggerated. So the void is tested by consistency, not by a single view. A second scene forms inside the hollow. A soft gradient of glow fills the space almost uniform. Across it, a few isolated smudges sit far apart. The smudges do not align into a clear thread. The gradient remains smooth as though a thin fog is present but nearly featureless. That fog is not ordinary dust. It is the faint background of distant light spread across space. If interior structure existed in abundance, the smoothness would break more often. More tiny patches would cluster. More unevenness would appear. Instead, the smooth field persists. That does not prove total emptiness. It points toward a low density of luminous tracers. Intergalactic medium is thin gas between galaxies, mostly hydrogen and helium. Like a faint mist, it is almost invisible unless light passes through. Like a clear gel, it can carry subtle gradients without obvious texture. It matters because even rare gas can add a soft haze to long paths. In denser regions that gas has slightly higher concentration, it can scatter light by a small amount. It can also absorb at specific energies, leaving delicate notches. In a wide hollow, the concentration tends to drop. The path becomes clearer. The background then arrives with less softening. The rim, by contrast, adds a whisper of extra scatter. The boundary becomes not only denser in galaxies, it becomes denser in the faint material that fills the spaces between them. A physical detail emerges. The rim can behave like a thin, layered curtain. The curtain thickens along the inner edge. It thins outward into the filaments. The inner edge looks sharper because the density gradient rises quickly. That sharp rise can be read through how quickly background patterns change across the boundary. A limit of observation returns in a calmer form. The background itself is not perfectly smooth. It has its own clumps and gaps at many distances. A patch of background structure can mimic a foreground wall. A foreground wall can hide behind a background gap. Separating the layers requires clean distance sorting. When that sorting is imprecise, contamination leaks between layers. The limit is therefore twofold. Faintness hides true objects, and depth, blur mixes unrelated ones. Both limits can create a false sense of clean emptiness. Yet both limits also leave telltale signatures. False emptiness changes with the layer selection. Real emptiness persists. A third slow scene lingers on the far rim. The rim is seen with older light. It looks slightly dimmer. Its knots appear less crowded. The difference is gentle. It still suggests that the void is not perfectly symmetric in time. One side may have grown earlier, the other may have drained more recently. That unlocks another point. A void can have a history, not just a shape. If the rim sharpens at a particular layer, it hints at when drainage becomes strongest. If the interior stays sparse across all layers, it hints at a consistently low content. The story remains quiet. The view shifts from what exists to when it exists. The scene then eases toward motion. If the rim is a layered curtain, then its material should drift outward slowly. If the interior is a long corridor, then its gradients should point toward the edges. The next step is to let the rim's gentle flows become visible through their patterns, and to see what the boundary's motion suggests. A boundary can be calm yet still reveal motion. In that region, the void's rim acts like a slow shoreline where gentle flows leave subtle patterns. The question is not whether anything moves. The question is how the movement is arranged. A void is not static. Material drifts outward from its interior. It does so unevenly. The rim becomes a place where paths converge. Peculiar velocity is motion relative to smooth cosmic expansion. Like foam on a river, it shows where currents twist beneath the surface. Like dust in a sunbeam, it reveals drafts that are otherwise invisible. It matters because a rim can look sharp for different reasons and motion can separate them. A slow, visual anchor forms along the boundary. A thin arc of galaxies curves like a pale bracelet around darkness. Along the arc, spacing is not uniform. Small clumps sit like beads. Between beads, the arc narrows. The narrowing is physical. It is a compression of where matter has collected. The inner edge of the arc looks steeper than the outer edge. That asymmetry is a clue. If outflow from the interior piles up strongly, the inner edge becomes sharp. If the rim is only a projection, the sharpness tends to smear both ways. A small payoff settles here. The shape of the gradient across the rim carries the story of how matter arrives. In the simplest picture, the interior pushes outward in a slow drift. It does not push like a forceful wind. It drifts as tiny accelerations add up over long time. The drift gathers near the boundary. The gathered matter thickens filaments. It also tightens the spacing of galaxies. If the drift is smooth and broad, the rim becomes thick. If the drift channels into a narrower band, the rim becomes thin. That channeling can happen if the surrounding filaments form a partial cage. The cage is uneven. Some directions are reinforced by thicker strands. Other directions are open. Flow then finds the easier exits. The rim sharpens where exits are less open. It softens where exits are wider. The scale shift is gentle. A single galaxy moves through its local environment over millions of years. A void boundary evolves over billions of years, yet the same logic applies. Motion leaves patterns. Patterns reveal gradients. In a galaxy, the pattern might be gas in a disk. In a void, the pattern is the distribution of many galaxies across a wall. A slow scene turns inward. The interior is dark. It is not featureless. A few faint points sit far apart. Their positions matter. If those points drift outward, their separation from the rim changes in a consistent way. If they are stationary relative to the rim, then the rim's sharpness must come from other causes. Another small payoff arrives. Even a sparse interior can act as a compass, because a direction of drift is enough to test the flow. In practice, that test meets a limit. Motion along the line of sight is hard to disentangle from distance inference. A small unknown in distance can mimic a large apparent motion. If the distance estimate is slightly off, a galaxy appears shifted along depth. That shift can be misread as a flow. The limit is therefore one of reconstruction. The true motion is three-dimensional. The evidence is projected and blurred. This limit matters most near a void rim where a small shift can move a tracer from interior to wall. A rim can look thinner if tracers are pushed outward by distance blur. A rim can look thicker if tracers are pulled inward by the same blur. The calm response is to look for patterns that survive these effects. If the rim's inner edge stays steep across many depth selections, it suggests genuine compression. If the steepness flips or fades, it suggests a measurement artifact. A new visual anchor arrives as a field of faint arcs. Background galaxies behind the rim are slightly stretched. The stretching lines tend to align tangentially around the boundary. That alignment is subtle. It still provides a consistent ring-like hint. It ties the visible ridge to a mass ridge. That resolves another question. A sharp rim is more convincing when light bending agrees with galaxy counts. The analogy shifts gently to something everyday and new. A rim under slow drainage resembles a coffee filter edge after water passes through. The center becomes clearer. Fine particles collect near the perimeter. The collection forms a thin, darker ring. The ring is not placed there by hand. It forms because flow carries what it can and leaves a residue where paths slow. The void's rim behaves similarly. Flow carries matter outward. Paths slow near surrounding structures. Matter collects, and the gradient sharpens. The analogy is not perfect. Space is not a liquid. Gravity is not a sieve. Yet the image clarifies the directionality. A slow outward drift can produce a thin boundary if the surrounding web confines it. Another payoff lands. A thin rim does not require a strange object inside. It can arise from ordinary flow guided by ordinary structure if the geometry is extreme. Yet geometry itself becomes the next question. How can the surrounding web produce a confinement strong enough to shape such a large hollow? How can a boundary remain sharp over a span that is enormous? The answer begins with the invisible scaffold. Visible galaxies are only tracers. Most mass is not luminous. If the invisible mass forms a tighter ridge, it can sharpen the visible ridge as well. If the invisible ridge is missing, then the visible sharpness may be deceptive. A final, slow scene rests on the rim again. The inner side falls away quickly, the outer side blends into a network of filaments. The arc of beads remains calm. The void remains still in appearance. Yet the idea of slow motion stays present. The next step is to follow the invisible scaffold itself. The next step is to treat the void not as empty light, but as a shaped absence of mass, and to see what that absence implies. Darkness can hide not only light, but also the weight that shapes light. In that region, the Boötes void becomes strange if the invisible mass is missing, as well as the luminous traces. The rim is visible as a thin band of galaxies. The interior is visible as wide separation and quiet spacing. Yet the deeper question sits beneath both. The question is how much mass remains when the lights thin out. A slow visual anchor settles on a broad patch behind the void. Countless distant galaxies appear as soft oval smudges. Near the void's edge, many ovals lean slightly in a shared direction. Their long axes seem gently combed into a shallow curve. Farther inward, the ovals relax toward random orientations. The change is delicate. It still suggests a boundary that affects passing light. Dark matter is mass that does not emit light inferred by gravity. Like a heavy stone under clear water, the surface ripples change without showing the stone. Like a buried root under soil, the ground bulges without revealing the root. It matters because most large-scale structure is shaped by that unseen weight. A small payoff arrives with the definition. Absence of light does not guarantee absence of mass. A void can be dim yet still hold a faint scaffold of invisible matter. That scaffold keeps the rim from collapsing into a thin line. It keeps the basin from becoming too perfect. In ordinary expectations, the interior is underdense, not empty. It contains less of everything, not none of the unseen mass. Gravity then remains present in a softer form. Light passing through the void should still experience gentle deflection. The deflection should be weaker than in a filament. It should not vanish entirely. Lensing is the quiet method that follows. Light behaves as a path that bends when space is curved by mass. The bending is tiny for each clump. Over long distances, many tiny bends add up. In a dense wall, the accumulation becomes measurable as a common shear. In a deep hollow, the accumulation should be reduced. The shear should loosen. A slow scene holds on the rim again. The galaxies on the boundary form a thin arc. The arc is not smooth. It has small knots where spacing tightens. Between knots, the arc thins. Behind it, the faint ovals appear slightly stretched tangentially along the arc. The stretch is like a soft brush stroke that follows the rim. That pattern unlocks another point. The rim is not only a line of lights, it is also a line of mass. If the void is truly extreme, the interior should show an even calmer shear. The background ovals should become less biased there. The transition from rim to interior becomes a gradient in distortion. The gradient is a physical detail, not an artistic one. It is the trace of curvature changing across space. A single number can steady the scale without crowding the ear. On cosmic scales, the unseen mass outweighs luminous matter by about 5 to 1, like 5 deep layers beneath one thin surface layer. That ratio is not measured inside the void directly. It sets a baseline expectation about how much invisible weight might remain even in dim regions. If the interior had almost none of that weight, the void would be more than a low-density basin. It would be a sharp deficit in the main ingredient of structure. That kind of deficit would strain ordinary formation stories. Another small payoff arrives here. The most suspicious emptiness is not the absence of galaxies. It is the absence of the gentle pull that should still remain when galaxies are rare. Yet that suspicion meets a calm limit of observation. The lensing signal in a void is inherently weak. It is a small average over many faint shapes. Each background galaxy has its own true shape. That true shape is unknown. only a slight statistical bias can be extracted. If background galaxies are sparse, the bias becomes uncertain. If their shapes are noisy, the bias becomes uncertain. Line of sight structure also intrudes. Mass in front of and behind the void can mimic a rim. A distant filament can add shear that looks like local curvature. A nearer clump can subtract or rotate the pattern. The limit is therefore not only faintness, the limit is the mixing of many depths into one projected measurement. The mind wants a clear map of mass. The sky offers only a layered overlap. Another slow visual anchor forms to soothe that complexity. A broad, dim bowl of the void interior sits like a shallow depression in a foggy plain. Along the bowl's inner wall, the background ovals change their preferred tilt by a small amount. The change is gradual. It is not a sharp switch. That gradualness is itself informative. A real mass deficit should produce a smooth relaxation of shear toward the center. A false deficit created by selection tends to produce patchy jumps. Patchiness comes from uneven sampling. Smoothness comes from a coherent large-scale geometry. A small payoff lands with that contrast. Smooth patterns are harder for chance to imitate across wide areas. Motion adds another angle without adding another core concept. The rim galaxies are expected to drift with peculiar velocities that reflect nearby mass. If invisible mass concentrates along the rim, the drift should correlate with the densest knots. If invisible mass is unusually absent, the drift becomes weaker and less organized. Yet the same observational limit returns. Depth uncertainty can mimic drift. A slight misplacement in distance can look like a line of sight motion. The difference is subtle. Consistency across many traces becomes the quiet judge. A region with a genuine mass ridge tends to show repeated alignments. A region with only projection tends to show alignments that wash out under different selections. Another analogy arrives and stays unique. The void's mass question resembles a calm valley after snowfall. The visible ridges appear where snow piles in sheltered lines. The deeper ground shape is inferred from how the snow surface curves. If the surface curves smoothly down in the valley, the ground is likely shaped that way. If the surface remains strangely flat, the ground might be missing a usual slope. The snow is not the ground. The snow still reveals the ground's influence. In the same way, background galaxy shapes are not mass. They still reveal mass through their faint alignment. The analogy remains gentle. Snow can drift by wind. Light does not drift by wind. Yet both are shaped by an underlying structure that is not directly seen. A third slow scene returns to the rim as a layered band. The inner edge drops quickly into darkness. The outer edge frays into filaments. The shear pattern behind it is slightly stronger along the tighter knots. The pattern loosens toward the interior. That loosening suggests a deficit rather than a hidden central pile. It does not prove an extreme absence. It supports the ordinary expectation of underdensity. It also keeps the tension alive in a soft way. The Boötes void can be large and still be ordinary in its invisible content, or it can be large and unusually empty in the very ingredient that shapes the web. The next step is to look for a different imprint, one that does not rely on counting faint shapes. The next step is to let the oldest background light carry a gentle signature of the hollow, and to see whether that signature agrees with the mass story. The oldest light in space is so smooth that a missing region can leave a soft bruise. In that region, a large void can imprint a faint cool patch on the ancient background glow. The imprint is not carved by dust. It is shaped by gravity and time. The cosmic microwave background is ancient light from the early universe. Like a thin fog of warmth, it fills every direction. Like a distant drumbeat, it stays steady while smaller noises come and go. It matters because later structures can nudge its energy slightly. A slow visual anchor forms as a wide, pale field of faint warmth. Across it, a long oval shadow appears. The shadow is not sharp. It is a gentle dimming with a smooth edge. It sits where the void lies along the line of sight. The dimming is small. It still carries a message. Light behaves as a traveller that can gain or lose a little energy. That energy shift happens when light crosses changing gravitational landscapes. Integrated Sachs-Wolf effect is energy change from evolving gravitational potentials, like a cart rolling through a valley while the ground slowly lifts, like a note drifting slightly in pitch when the air pressure changes. It matters because a large void can alter the balance between entry and exit. In a static landscape, a photon enters a potential well and loses energy. It exits and gains the same amount back. The net change is near zero. In an expanding universe, the landscape evolves during the crossing. A deep hollow can become shallower while the light is inside. Then the light does not regain all it lost. It exits with a small deficit. That deficit appears as a cooler patch in the ancient glow. A small payoff arrives with that sequence. A void can be tested without counting galaxies by watching whether ancient light leaves slightly dimmer. Another slow scene settles into the void itself. The interior is a wide cavity. The rim is a thin band. The gravitational landscape across it is a broad bowl. The bowl is made of missing mass relative to surroundings. The rim is made of piled mass. As light enters the bowl, it falls into a shallower pool than in a dense region. The fall is still real. The rise out is also real. The difference is the timing. The crossing takes long. For a hollow hundreds of millions of light-years wide, the crossing time is hundreds of millions of years. That is like watching a slow tide shift the shoreline during a single crossing of a bay. If the potential changes during that crossing, the ancient light remembers it. The scale shift is gentle and steady. The imprint is a broad patch on a sky map. The cause is a mass deficit spread across a volume so large it dwarfs clusters. The effect on each photon is tiny. It is far smaller than a single blink in ordinary terms, yet the effect is coherent across an enormous area. That coherence is the power. Another small payoff settles here. Enormous size can turn tiny changes into detectable patterns because many photons share the same history. The physical detail becomes the gradient of the patch. A void imprint should have a smooth center. It should fade outward. The fade should be gradual, not jagged. The rim can add a slight ring-like feature. The ring would not be bright. It would be a subtle change in slope. The center cools gently. Near the rim, the cooling can level, then it relaxes back. The exact shape depends on how the missing mass is distributed. If the void is truly extreme, the patch can be stronger than expected. If the void is ordinary, the patch is weaker. The limit of intuition arrives softly. The ancient background is not perfectly uniform. It has its own primordial ripples. Those ripples are larger than the void imprint in many directions. The imprint is searched for by correlation across many regions. One region can mislead. A random primordial cold spot can sit near a void by chance. Another limit comes from the void itself. The depth profile is inferred. If the void is not spherical, the imprint changes shape. If there are hidden filaments inside, the imprint weakens. The limit is therefore one of separation. The observed patch is a mixture of primordial variation and late-time effects. Untangling them requires careful statistical handling. It is a quiet challenge. Another slow visual anchor returns to the pale field. The oval shadow is compared to its surroundings. Nearby other faint patches appear. Some are warmer, some are cooler. The void-aligned patch stands out only in its alignment with the known hollow. That alignment is the key. It asks a specific question. Does the ancient glow show a consistent dimming along the same line? If it does, the void's mass deficit is confirmed in a different way. If it does not, the void may be less extreme than its galaxy count suggests. Another payoff arrives in that framing. Multiple weak tests when they agree can outweigh any single dramatic appearance. A new everyday analogy arrives and stays unique. The imprint resembles a faint indentation on a quilt after a heavy object is removed. The quilt is smooth and warm. The indentation lingers as a gentle depression. It is not a hole. It is a memory of a change in pressure. The object does not need to be seen. The quilt tells the story through shape. In the same way, the ancient glow tells a story through a subtle energy shift. The glow is not a photograph of the void. It is a record of the crossing. The analogy stays calm. A quilt returns to flatness with time. The background glow does not relax. It simply carries the pattern forward. A third slow scene focuses on the rim as a thin band again. Behind it, the ancient patch may show a slight change in slope. That change can hint at where the piled mass sits. If a mass ridge is concentrated, the slope change is tighter. If the ridge is broad, the change is softer. That guides the next checkpoint. It asks how gas and faint material behave at the rim. It asks whether the interior truly lacks structure, or whether structure is present but dim. The story remains gentle. The imprint on the ancient glow is a quiet companion to lensing. Lensing traces curvature through background shapes. The ancient glow traces energy shifts through vast time. Together they suggest whether the void is ordinary underdensity or an extreme deficit. The next step is to move from ancient light to the faint material inside the hollow. The next step is to watch gradients in rare gas and see whether the interior is truly smooth or softly layered. A void can feel empty, yet still carry faint layers like breath on cold glass. In that region, rare gas inside the Boötes void becomes a quiet tracer of structure, even when galaxies are scarce. The interior is not a perfect vacuum. It is a low-density medium. It holds hydrogen and helium spread thin. Over long distances, even thin gas leaves patterns. It does so through gradients and subtle absorption. The patterns are gentle. They still reveal whether the hollow is smooth or quietly threaded. A slow visual anchor forms as a dim beam of light passes through the void. Along the beam, the darkness is not uniform. It shows faint bands like thin smoke sheets. Each band is slightly denser than its neighbour. The bands are wide, their edges are soft. The beam then reaches the rim and the bands compress into a tighter stack. The stack looks like layered gauze at the boundary. Intergalactic medium is thin gas between galaxies, mostly hydrogen and helium. Like mist in a valley, it can be present without obvious brightness. Like clear syrup, it can hold gradients that only show when something passes through. It matters because gas responds to gravity and expansion, so it outlines slow flow. A small payoff settles with that. A void interior can be mapped without relying on bright objects because gas can whisper where mass has been. In dense regions, gas clumps and cools into richer structures. In voids, gas stays warmer and more diffuse. It spreads into broad sheets. It forms gentle filaments. Those filaments can be too faint to show as visible light. They still affect passing spectra through narrow absorption features. The effect is not a sharp blackout. It is a set of fine notches. The notches appear at specific stretched wavelengths. Their positions sort the gas by distance. Their depths hint at density. A calm number can anchor the scale without clutter. The typical density of this gas is about 1 atom in a cubic meter, like a single grain of dust spread through a room-sized box. That comparison is imperfect. Dust is heavier and visible. The idea is spacing. The gas is so sparse that emptiness feels natural, yet across hundreds of millions of light-years that sparse material sums into real columns. A beam crossing the void intersects countless cubic meters. The total becomes enough to leave a measurable trace. Another small payoff arrives. Vast distance can turn almost nothing into something because accumulation is patient. The physical detail becomes the gradient across the rim. Gas density rises toward filaments. It rises more sharply near the wall. So an absorption pattern can show a slow ramp. It can show how quickly the ramp begins. If the void has a thin boundary, the ramp is steep. If the void has a broad boundary, the ramp is shallow. The ramp is a boundary shape in gas, not only in galaxies. A slow scene turns inward again. The interior shows occasional stronger bands. They are isolated. They do not form a rich network. Their spacing is wide. Their edges blur into the surrounding low-density medium. This arrangement suggests a web that is present but faint. The web is not absent. It is diluted. That resolves one quiet question. A void does not need to be perfectly empty to look empty in light. It can contain a ghost lattice of gas too thin to shine. A scale shift continues smoothly. A single absorption notch is narrow. It is a fine feature within a broader spectrum. Yet that notch can correspond to a sheet of gas spanning millions of light years. The smallest mark can imply the largest sheet. That mismatch is where intuition can slip. The mind expects large things to look large. Here the large becomes small in representation. The limit of observation is tied to that representation. Absorption measurements depend on bright background sources. If the background is too faint, the notches vanish into noise. If the spectral resolution is coarse, narrow features blend into a shallow depression. Multiple weak bands can merge and mimic a single stronger one. Another limit comes from temperature and ionization. Gas can be present, but in a state that produces fewer notches. The absence of a notch does not guarantee absence of gas. It can indicate gas that is too hot or too ionized to mark that wavelength strongly. The limit is therefore interpretive. The measurement sees only particular states of gas. The void may hide material in states that are harder to trace. A small payoff settles here. Gas traces are selective. They show a biased slice of what exists. So the interior must be inferred from a combination of patterns, not from one missing line. A new everyday analogy arrives and stays unique. The void gas resembles the faint scent left in a large corridor after a single drop of perfume evaporates. The scent is thin. It is nearly invisible to ordinary senses, yet it forms gradients. It pulls slightly in corners. It becomes stronger near a doorway where air currents slow. The corridor remains empty of objects. The air still carries information about flow. In the same way, the void remains empty of rich structure. The gas still carries information about slow drainage and confinement. The analogy is gentle. Scent spreads by diffusion. Gas in space responds to gravity and expansion. The shared idea is gradient, not mechanism. Another slow visual anchor forms as a set of translucent sheets drift within the hollow. The sheets are broad. They are nearly parallel. They tilt slightly as they approach the rim. Their tilt suggests a gentle funneling. The rim then appears as a thicker stack where sheets overlap. The overlap creates a denser layer like a faint seam. That seam is a physical boundary in gas. It supports the earlier idea of a layered curtain at the rim. Another payoff arrives. A thin rim in galaxies can be reinforced by a thin rim in gas because both respond to the same scaffold. If gas gradients align with lensing gradients, the case strengthens. If they do not align, the sharp rim may be partly apparent. The story remains calm and incremental. The void is now seen through three lenses. Light from galaxies traces what shines. Background shapes trace what bends light. Absorption traces what lies between. All three can agree on a simple picture. The interior is underdense and smooth. The rim is thin and layered. Or they can disagree and reveal hidden complexity. The next step is to move from gas to the faint fields that thread it. The next step is to see whether magnetism and charged particles outline a skeleton inside the hollow. or whether the interior remains almost featureless in every tracer. A void can carry invisible threads that do not glow yet still guide faint motion. In that region, weak magnetic fields and rare charged particles can outline structure inside the Boötes void. The interior may look smooth in light. It may still be threaded by fields. Those fields do not need to be strong. They only need to be coherent. When charged particles drift through a field, their paths curve. When many particles do this, a faint glow can appear. The glow is not a spotlight. It is a thin wash that traces direction. A slow, visual anchor forms as a dim ribbon crosses the void interior. The ribbon is long and narrow. It curves gently toward the rim. Its brightness is barely above the background. Along its spine, the ribbon has a brighter core. Around that core, a fainter sheath spreads out. The sheath fades in a smooth gradient. The ribbon looks like a strand of smoke in still air, but it holds a persistent shape. Magnetic field is a region where moving charges feel a force. Like grain in wood, it sets a preferred direction even when unseen. Like a comb line in hair, it organizes strands without adding material. It matters because directionality can exist even in low-density space. Synchrotron emission is faint radio glow from particles spiraling in magnetic fields, like a soft hum that follows a curved wire, like a whisper that grows where paths tighten and bends. It matters because the glow traces both particles and the fields guiding them. A small payoff arrives with the definitions. Fields can reveal a skeleton that galaxies do not show, because fields can span gaps where matter is too thin to shine. In dense filaments, magnetic fields are expected to be stronger. They can be amplified by turbulence and compression. In void interiors, fields are expected to be weaker. They still might not be absent. They can be stretched and diluted yet remain coherent over large scales. If a void is unusually empty, the field could be even weaker. If the void contains faint filaments of gas, the field could cling to those filaments and become visible through a thin glow. That framing matters because it offers a different kind of tracer. Gas absorption shows where atoms sit. Lensing shows where mass curves space. Synchrotron glow shows where charges spiral and where fields align. If all three agree, structure becomes harder to dismiss. A slow scene settles on the void rim again. The boundary is a thin arc of galaxies. Just inside the arc, the dim ribbon seems to run parallel for a distance. The ribbon then bends inward. The bend is smooth. It suggests a flow channel rather than a random patch. Along the bend, the ribbon's core brightens slightly. The brightness change is a physical detail. It implies compression or a thicker particle stream. That unlocks another point. A rim can act like a guide rail, shaping not only matter flow, but also field geometry. Compression at the boundary can tighten field lines. Tightened field lines can make particles radiate more efficiently. The result can be a faint halo or rim-aligned glow. The halo would not be uniform. It would be brighter near knots where filaments meet. It would fade between knots. The fading would follow the same bead-like rhythm seen in galaxies but in a softer register. A calm number can anchor scale without clutter. A typical void magnetic field may be around a trillionth of a unit used for strong fields, like a breath compared to a steady wind. The exact value is uncertain. The comparison is the point. The field is so weak that its direct force is small. Yet over enormous distances, even weak guidance can shape particle paths. That is the scale shift. A particle spirals on a tiny radius around a field line. The same field line can extend for millions of light years. A microscopic curve and a cosmic span share one geometry. Another small payoff settles here. Small forces can matter when the path is long because the guidance is continuous. A limit of observation arrives softly. The glow is extremely faint. It sits beneath brighter foregrounds from other regions. It can be confused with diffuse emission that is not related to the void at all. Resolution also matters. A narrow ribbon can blur into a broader haze. A broad haze can hide a narrow filament. Another limit comes from the particles themselves. Charged particles lose energy. Their lifetimes depend on their energy and environment. A region may have a magnetic field but too few particles to reveal it. Another region may have particles but weak fields that keep the glow below detectability. The absence of glow therefore does not prove the absence of field. It can mean the tracer is missing. This limit matters because the void is defined by scarcity. Scarcity makes every test partial. Another slow visual anchor forms as a wide, faint halo around the rim. The halo is not a sharp ring. It is a soft band. It thickens near the densest knots. It thins between them. The band's inner edge is slightly steeper than its outer edge, echoing the galaxy rim gradient. That echo clarifies a small question. If the field and particle glow share the same asymmetry as the galaxy wall, then the boundary is a true compression zone. The compression zone is not only luminous matter, it is also plasma and field geometry. A new everyday analogy arrives and stays unique. The field within the void resembles the grain pattern inside a clear block of ice. The ice looks transparent and empty. Inside, fine lines reveal flow and freezing history. The lines do not add bulk. They guide cracks and reflections. In the same way, a void can look empty. Inside, fine magnetic alignment can guide particle paths and faint emission. The analogy stays gentle. Ice forms quickly. Cosmic fields evolve slowly. The shared idea is a hidden direction. Another payoff settles with that analogy. Direction is information. It can persist even when matter is thin. Now the question becomes what the direction implies about the void interior. If the ribbon-like features exist, the interior contains faint filaments. Those filaments could host gas sheets and weak mass ridges. If the interior shows no coherent glow, the interior may be closer to smooth dilution. Either result feeds back into the earlier tests. A void with inner filaments should show more absorption bands. It should show slightly less extreme underdensity in lensing. It might show a softer imprint on the ancient background. A void without inner filaments should show the opposite. The scene eases toward the next checkpoint. The next step is to use the few interior galaxies if present as clocks of environment. The next step is to see whether rare islands inside the hollow carry signatures of slow isolation, and whether their distribution fits a truly empty basin or a faintly threaded one. A few lights inside a great hollow can say more than 1,000 lights on its rim. In that region, rare galaxies within the Boötes void act as environmental clocks that reveal how isolation shapes what still forms. The interior is sparse, it is not blank. A small number of islands remain. Each island is surrounded by long distances of thin gas and weak tides. That setting changes how matter settles. It changes how gas cools. It changes how stars accumulate in a quiet way. A slow visual anchor forms around a single faint galaxy inside the void. It appears as a smooth oval glow. Its edges fade gently into darkness. A thin dust lane is absent or extremely subtle. The light looks evenly spread with a soft gradient from center to edge. Nearby, nothing obvious crowds it. The nearest faint smudge sits far away, separated by a wide black interval. The scene is calm. It still carries information. Star formation is the process of gas collapsing into new stars. Like dew gathering into droplets in still air. Like flour clumping when a small splash lands forming grains from dust. It matters because the rate of new stars depends on gas supply and disturbance. In dense regions, galaxies are jostled. They can pull gas inward. They can trigger bursts. In a void, those triggers are rare. Gas arrives slowly. Encounters are uncommon. so a void galaxy can age quietly. Its colour tends to shift redder as fewer new blue stars form. Its shape can settle towards smoothness if no strong tidal tug disturbs it. A small payoff settles with that. A void galaxy is not only an object, it is a record of calm conditions. Another slow scene shifts to a second interior island. This one is smaller and fainter. Its outline is irregular. A faint patchiness appears in its light distribution. The patchiness hints at small pockets of gas still forming stars. The pockets are widely spaced. They do not form grand arms, they form isolated knots. Around them, the rest of the galaxy remains dim. This contrast unlocks another point. Isolation does not always stop star formation. It changes its rhythm. It becomes intermittent. It becomes localized. It depends on whether gas remains and whether it can cool. Cooling time is how long hot gas takes to radiate heat away. Like soup left to cool, it takes longer in a large pot. Like a warm stone at night, it loses heat slowly when the air is still. It matters because gas that stays warm resists collapse into dense clouds. In a void, gas density is low. Low-density gas cools less efficiently. It can remain warm for long spans. That warmth can stall star formation. Yet if a small region becomes slightly denser, it can cool faster and form stars in small bursts. The environment therefore selects for subtlety, not grand fireworks, small scattered knots. A calm number can anchor scale. A typical separation between interior galaxies can be tens of millions of light-years, like isolated cabins spread across a continent-sized plane. The comparison is imperfect. Cabins are placed with intent. Here the placement reflects the web. Still, the spacing conveys the idea. Tidal influence weakens with distance. So each galaxy evolves with less external stirring. That is the scale shift. Inside a galaxy, gas clouds form and collapse on spans of millions of years. Across the void, the environment changes over billions of years. The internal rhythms continue. The external triggers fade. Another small payoff arrives. When external influence drops, internal processes become the dominant sculptors. The physical detail becomes the galaxy's light profile. A smooth gradient suggests settled structure. A patchy gradient suggests active pockets. A sharp central peak can suggest a dense central component. A broader center suggests a more diffuse distribution. These details are calm clues. They do not require dramatic events. They are shaped by how gas arrives and how it cools. In void interiors, gas may accrete along faint filaments. If those filaments exist, the few galaxies may align subtly along them. Their positions may trace a ghost line. If no filaments exist, positions may appear more random within the basin. A slow visual anchor forms as three faint galaxies appear in a loose line. The line is not perfect, it is gentle suggestion. Between them darkness stretches. Around them faint absorption bands hint at a thin gas sheet. The sheet is nearly invisible, it still implies a path for gas supply. That resolves a quiet question. If interior galaxies align, then the void is not a pure cavity. It contains a faint skeleton. The limit of observation arrives softly. Interior galaxies are faint and rare. Sampling is sparse. A few points can form a line by chance. A faint galaxy can be missed entirely due to visibility thresholds. Distance uncertainty can move a point along the depth axis. A true alignment can be smeared. A false alignment can be created. The limit is therefore statistical. The interior cannot be described with confidence from a handful of objects. It requires careful aggregation across many traces. Even then, the void is unique enough that general rules can mislead. Another limit comes from classification. A smooth light profile can be created by true age. It can also be created by faintness and blur. A patchy profile can be real. It can also be noise in low signal. The limit is resolution. Fine structure can vanish. Yet some features persist. A strongly red colour across the whole galaxy suggests long quiescence. A strong central concentration suggests a settled mass distribution. Those are less sensitive to fine resolution. Another small payoff settles here. The most reliable clues are broad patterns that do not depend on seeing tiny details. A new everyday analogy arrives and stays unique. A void galaxy resembles a small garden in a wide dry field. The garden can still grow. It grows slowly. It depends on a thin trickle of water that arrives along a hidden channel. When the channel is steady, growth is gentle and continuous. When the channel is intermittent, growth appears in patches. The field around the garden remains empty. The garden still carries signs of how the channel behaves. The analogy is calm. Gardens are managed. Void galaxies are not. The shared idea is supply. Another slow scene returns to the rim as a reference point. The rim galaxies are crowded. Their shapes are more disturbed. Their light profiles show more variety. The contrast between rim and interior becomes a gentle measurement of environment. If interior galaxies look too similar to rim galaxies, then the interior may not be as isolated as it appears. If interior galaxies are consistently more quiescent and more smooth, then the void environment is confirmed as quiet. That confirmation feeds back into the broader mystery. A void that is truly empty would produce strong isolation signatures. A void that contains hidden filaments would produce mixed signatures. The story remains soft. The next step is to return to the mass map in a deeper way. The next step is to examine the background distortions for lattice-like hints, and to see whether a hidden frame exists inside the hollow, faint yet coherent. A pattern can be present even when nothing bright draws it. In that region, the void can be tested for a hidden frame by looking for a faint lattice in how background shapes distort. The method is gentle. It does not search for objects. It searches for coherence. If a thin skeleton of mass threads the interior light should carry a faint memory of it. If the interior is truly smooth, that memory should be absent or purely random. A slow visual anchor forms as a wide field of distant galaxies fills the view. Each galaxy is a tiny oval. Most are slightly blurred. Across the field, the ovals show a weak but organized shear. Near the rim, the shear curves along the boundary. Deeper inside the shear hints at a subtle grid. The grid is not sharp. It is a whisper of alignment that repeats across many ovals. Gravitational shear is the small stretching of background images by mass. Like fabric pulled gently, it lengthens in one direction. Like wet paint dragged by a soft brush, it leaves a consistent streak. It matters because shear can map mass where light is absent. Convergence is the focusing effect that slightly magnifies images. Like a lens that gathers light, it makes things appear larger. Like a slow swell under a sheet, it changes size without changing the pattern. It matters because convergence traces over and under density as a smooth field. A small payoff arrives with these terms. A void can be mapped by the shape of distortion fields even when individual bends are tiny. Shear responds strongly to gradients in mass. Convergence responds to the total mass along the line of sight. If the void is an extreme deficit, convergence dips smoothly across its interior. If the void contains faint inner filaments, shear can show faint ridges and saddles. These ridges would not look like bright lines. They would appear as subtle changes in the direction of stretching. The physical detail is the curl and twist of these direction lines. A true filament produces a shear pattern that wraps around it. A true junction produces a saddle where stretching changes orientation. A smooth hollow produces mostly radial or tangential patterns around the rim with little internal structure. Another slow visual anchor settles into the interior. A set of contour lines is imagined in the shear field. The lines are not drawn. They're inferred by how the ovals align. Inside the void, one contour bends and then bends again. A second contour runs roughly parallel, then diverges. The spacing between them changes gradually, like a gentle squeeze and release. That pattern unlocks a point. A coherent interior structure, even if faint, would produce repeated bends in the same places across different samples. Random noise would not. The scale shift remains steady. Each background galaxy provides one noisy measurement. The void interior spans a volume so large that countless such measurements can be combined. The combination is like averaging many faint whispers. One whisper is meaningless. Many whispers can reveal a consistent phrase. This is where the method becomes powerful. Yet it is also where limits appear. The signal is weak. Shape noise is large. It is the natural variety in galaxy forms. That variety can overwhelm small shear. The limit is therefore statistical. It requires many background sources. It requires careful weighting. It requires that the selection does not accidentally prefer certain orientations. Another limit comes from depth overlap. Mass outside the void can add shear that masquerades as internal filaments. A foreground ridge can project across the interior. A background cluster can create a saddle. The limit is line of sight contamination. The distortion field is a sum of many depths. Untangling those depths is hard. Another small payoff lands here. A hidden frame inside the void is only meaningful if it persists after subtracting the expected contributions from outside structures. A calm number can anchor the method. To see a weak shear signal, many thousands of background galaxy shapes may be needed, like needing thousands of raindrops to measure the average direction of a very light breeze. The exact count varies. The comparison conveys patience. A light breeze does not move every drop the same way. It produces a small bias. Many drops reveal it. In the same way, a void's internal skeleton would not stretch every galaxy clearly. It would bias the average. The physical detail returns to the rim. The rim is thin and layered. If the rim is a true mass ridge, the shear near it should show a sharper gradient. The orientation field should rotate quickly across the boundary. That rotation is like a hinge. On the outside, stretching aligns with filaments. On the inside, stretching relaxes. A quick rotation implies a tight ridge. A slow rotation implies a broad wall. That resolves a quiet question. The rim thickness can be tested independently of galaxy counts by the steepness of shear rotation. A new everyday analogy arrives and stays unique. The shear field resembles the pattern of ripples on a pond when a gentle current passes under floating leaves. Each leaf is free to face its own direction. A weak current biases them slightly. When many leaves are seen together, a flow line appears. The flow line reveals eddies and channels without showing the water itself. The analogy is calm. Leaves have size and drag. Galaxies have shape and distance. The shared idea is biased orientation revealing invisible flow. Another slow visual anchor forms as the interior shear field shows faint repeating channels. One channel curves toward the rim, another crosses it at a shallow angle. Where they intersect, the shear direction changes more abruptly. That intersection resembles a node in a hidden mesh. It does not require a bright galaxy cluster. It requires only a slightly denser thread of unseen mass. If such intersections exist, they imply that the void is not empty in its scaffold. It is only underdeveloped. Its web is thin. If no such intersections persist, the void may be closer to a smooth deficit. Another payoff lands. The difference between an empty basin and a thin mesh is not only philosophical. It changes the expected gas sheets, the magnetic alignment, and the isolation of interior galaxies. Those earlier tests begin to converge. If absorption bands show sheet shear should hint at ridges. If synchrotron ribbons appear, shear should hint at guiding mass. If interior galaxies align, shear should show a faint channel. Agreement would be a quiet strengthening. Disagreement would point to limits or to missing traces. The limit of observation returns once more in a softer tone. Even a true thin mesh can be below detectability. The interior could hold structure that is real but too weak to imprint on background shapes clearly. In that case, the absence of a lattice is not proof of smoothness. It is only a statement about sensitivity. That sensitivity depends on depth separation and on noise. It depends on the density of background sources. It depends on the size of the void's imprint on the sky. The calm conclusion remains stable. The void can be mapped as a field, not as a set of objects. The field can be smooth or lightly textured. Either way, the rim remains a key feature. It is the strongest gradient. It is the place where fields, gas, and galaxies gather. The next step is to widen the view toward rarer explanations that still leave geometric signatures. The next step is to consider whether repeating cell-like patterns or unusual symmetries could explain a sharp boundary without a typical interior mesh. A shape repeated in the cosmos can feel like a design even when it is only geometry. In that region, unusual symmetry is tested by searching for repeating patterns around the void rather than a single dramatic boundary. The rim looks thin, the interior looks quiet. Those traits can arise naturally. They can also hint at a larger arrangement that repeats. If the void is part of a broader cellular network, nearby voids and filaments should echo its scale and spacing. If it is a one-off extreme, the neighborhood should look less regular. A slow, visual anchor forms as a wide panorama of the cosmic web surrounds the hollow. Several dark basins sit in the distance. Between them, pale filaments form arcs. Where arcs meet, knots appear. The arrangement resembles a foam of bubbles frozen in place. Some bubbles are large, some are small. The Boötes region holds one of the larger basins. The question is whether its size is an outlier or part of a rhythm. Baryon acoustic oscillation is a preferred separation scale in galaxy clustering. Like ripples from an ancient splash that leave a faint ring in a pond. Like a gentle beat in music that persists beneath the melody. It matters because it introduces a subtle regularity in how matter is spaced. In large surveys, this regularity appears as a broad bump in correlation. It does not draw a single ring in the sky, yet it suggests that certain separations are slightly more common. A small payoff settles here. If a void seems to match a preferred spacing, it may feel less mysterious. It becomes a large feature resting within a known rhythm. The physical detail is the rim curvature and the spacing of surrounding knots. A foam-like network tends to produce walls that curve smoothly. It tends to produce junctions at angles that are not random. It tends to produce a distribution of cell sizes that is broad but not limitless. So the test becomes a calm measurement of context. Are there similar walls at similar distances? Are there other large basins nearby? Do filaments around them share a similar thickness and curvature? A gentle number can anchor scale. A preferred separation in the large-scale pattern is about 500 million light-years, like a repeated spacing between wide ocean swells. That does not mean every feature follows it. It means the universe has a faint tendency to echo that scale. If a void's diameter sits near that scale, it may be less surprising. If it is much larger, then it becomes rarer. The scale shift remains calm. A small statistical bump becomes a visible influence on the arrangement of enormous structures. Another slow scene settles on two nearby basins. Their rims appear as pale arcs. The arcs seem to sit at comparable distances from a central region. The comparison is not perfect. It is not a precise circle, yet a faint repetition appears. That repetition unlocks another point. Regularity does not require perfect symmetry. It can be a weak preference that emerges only when many regions are considered. This is where the limit of observation enters softly. The Boötes void is a single region. A single region cannot establish a universal pattern. It can only be compared against ensembles, yet ensembles require large uniform surveys. If the survey coverage is uneven, apparent gaps can be created by missing data. If the depth sampling changes with direction, the size of basins can be misestimated. The limit is survey completeness. Another limit comes from projection. A basin may appear larger if its boundaries are aligned along the line of sight. A basin may appear smaller if it is sliced by a survey edge. The void's perceived symmetry could be partly a selection effect. Another small payoff settles here. A claim of special geometry must survive the test of different cuts through data and different methods of defining boundaries. A new visual anchor forms around the void rim as a set of arcs traced by galaxy density. The arcs are measured by smoothing the counts over large angles. The result is a broad wall. Its thickness varies. In some sectors it is thin, in others it is thicker. That unevenness weakens the idea of a perfect cell wall, yet it does not eliminate a cellular context. Foam naturally produces uneven walls. Wall thickness depends on how much mass drains there. Junctions become thicker. Side walls remain thinner. This difference becomes a quiet clue. If the Boötes rim is thin everywhere, it may be unusual. If it is thin in some places and thick in junctions, it fits a foam picture. Another payoff arrives. The most telling feature is not a single boundary. It is the distribution of thickness around the boundary. The analogy shifts gently and stays unique. The neighbourhood resembles a sheet of drying soap bubbles. Each bubble is not identical. Some merge, some shrink. The edges thicken where many bubbles meet. The edges thin where only two meet. The pattern looks organised without being designed. In the same way, cosmic voids can form a foam. The web boundaries thicken at nodes and thin along walls. The interior of each cell stays sparse. The analogy is calm. Soap bubbles form by surface tension. Cosmic foam forms by gravity and expansion. The shared idea is cellular partitioning. Another slow scene turns back to the Boötes basin in that foam. If it is simply a large cell, it should have neighbouring cells of comparable order. It should have walls that connect to a network rather than ending abruptly. The filament should form a closed or nearly closed boundary in 3 dimensions, even if parts are faint. If the Boötes rim appears closed but the interior remains exceptionally clean, then it becomes a rare combination. Large and clean at once. That is where the phrase of something that should not be there begins to take shape. Not as a monster, but as a statistical tension. Another limit of intuition appears softly. Human pattern recognition leans towards symmetry. It finds circles and grids even in noise. In a sparse tracer field, chance alignments can look like rings. In a patchy survey, boundaries can look closed. The limit is cognitive bias. It matters because the void invites large shape stories. The calm response is to rely on quantitative measures of correlation and wall thickness. These measures reduce the temptation to see perfect cells. Another payoff settles. A void can be surprising without being unnatural. It can sit at the tail of a distribution. It can be large because the local environment permits long drainage. It can be clean because few filaments cross it. Yet the tail has a cost. If a void is too large and too clean, it becomes a constraint on models of structure growth. It asks whether the initial fluctuations in that region were unusually low. It asks whether the surrounding web geometry amplified the drainage. It asks whether something in the local neighbourhood delayed the formation of interior filaments. The story remains gentle. The next step is to explore how rare a void of this character might be under ordinary initial conditions. The next step is to treat the Boötes region as a probability problem, and to see whether the quiet tale of chance is enough. A rare event can be quiet in form like a calm dip that still changes a whole map. In that region, the Boötes void becomes a probability question about how often extreme hollows arise from ordinary beginnings. The rim is thin, the interior is clean. Those features can appear by chance. They can also signal that the local initial conditions were unusually low. The task is to treat the void as a tale of a distribution, not an exception carved by a new rule but a rare outcome under known rules. A slow visual anchor forms as a vast field of tiny density ripples stretches across early space. The ripples are gentle. They look like faint hills and shallow basins. Over time, hills grow into filaments. Basins expand into voids. One basin in this field starts slightly lower than the others. Its edges begin to drain matter away. Its interior becomes emptier. Its rim becomes sharper. The basin is not dramatic at first. It becomes dramatic only after long growth. Gaussian fluctuation is a random deviation with a bell-shaped probability. Like small variations in flour, when it is sifted, some spots are thicker. Like gentle dimples on a sand surface after a light breeze, most are small, and a few are deeper. It matters because the early universe is often modelled as many such random deviations. Cosmic variance is the idea that one region can differ from another by chance, like one patch of fog being thicker than another even in the same valley, like one stretch of ocean being calmer even under the same sky. It matters because a single large void might be a chance draw from a random field. A small payoff settles here. A void can feel special and still be consistent with the statistical tail if the tail is expected and the sample size is large enough. The physical detail is the rim steepness as a consequence of initial depth. A slightly deeper initial basin drains matter more effectively. Matter flows outward. The rim collects it. The inner gradient steepens. The boundary becomes layered. The interior stays more uniform. In that picture, a thin rim is not a separate mystery. It is the natural outcome of stronger drainage. The scale shift continues calmly. The initial ripple might be a small fraction of the mean density. It is a subtle dip on an early map. Over billions of years, that subtle dip expands into a cavity hundreds of millions of light years wide. A small difference at the start becomes a large difference at the end. Another small payoff arrives. The universe amplifies gentle beginnings when time is long and gravity is patient. A calm number can anchor the idea of rarity. A 2 in 1,000 fluctuation is rare, like finding 2 unusually low coins in a jar of 1,000 mixed coins. The number is an example, not a measurement of Boötes. The point is tail behavior. In a very large volume, even rare deviations occur somewhere. The question then shifts. Is the observed void consistent with a plausible tail given the surveyed volume? If a survey covers enough volume, a rare void is expected. If it covers too little, the void becomes more surprising. Another slow visual anchor forms as a long strip of survey volume is imagined. Along the strip, many smaller voids appear. A few medium voids appear. One very large void appears. The distribution is uneven. It has a long tail. Most voids are modest. The largest void is far larger than the median. This pattern unlocks another point. Long-tail distributions produce occasional giants without needing new physics, yet size alone is not the only variable. Cleanliness matters. A large void can still have interior filaments. A clean void implies not only an initial dip, but also a lack of later filament formation within it. That can happen if the initial field inside the basin is unusually smooth. It can also happen if surrounding structures siphon away material efficiently. The limit of observation enters softly. Void size depends on definition. Different algorithms can merge adjacent basins into one larger basin. They can also split one basin into several. The measured diameter is therefore not absolute. It depends on tracer density. If traces are sparse, small internal ridges can be missed, making the void appear smoother and larger. If traces are dense, those ridges are found breaking the void into subvoids. The limit is resolution in tracer sampling. Another limit comes from edge effects. A survey boundary can cut across structures and make gaps. A gap can mimic an extension of a void. Depth-dependent selection can thin traces farther away and exaggerate emptiness. These are quiet dangers. They make the probability question harder. Another small payoff settles here. Before rarity can be claimed, measurement definitions must be stable across methods and depths. A new everyday analogy arrives and stays unique. The void resembles a large clear patch in a loaf of bread where air pockets grew and merged during rising. Most holes are small, some are medium. Occasionally, several holes merge into one large hollow. The hollow feels surprising when seen alone. In a whole loaf, it can be expected. The analogy is calm. Bread rises quickly. Cosmic structure grows slowly. The shared idea is merging and tail outcomes. Another slow visual anchor returns to the rim as the evidence of merging. If several smaller voids merge, the rim might show seams. Seams would appear as slight changes in curvature. They would appear as thickness variations along the wall. A merged void might have a rim that is not uniformly steep. A single basin grown from one initial dip might show a smoother, more coherent wall. This difference offers a path forward. Rim texture can hint at formation history. Another payoff lands. The wall is a memory of how emptiness assembled. If it assembled by merging, the wall is more complex. If it assembled by clean drainage, the wall is more coherent. The probability question also feeds back into the earlier lattice search. If the interior is truly smooth, it suggests an unusually quiet initial patch. If the interior contains a thin mesh, it suggests ordinary initial conditions with delayed growth. Both can be rare in different ways. The story remains soft. The void can be an extreme but natural product of random beginnings, or it can be an extreme that strains typical expectations about how many such beginnings occur in a given cosmic volume. The next step is to widen the time axis further. The next step is to consider how the void evolves into the future, and whether its emptiness deepens, stabilizes, or gradually fills with faint structure. A void does not stay the same even when it looks still. In that region, the Boötes void is shaped by a slow future, in which expansion stretches distances while matter continues to drift toward the rim. The interior remains underdense. The rim remains a collecting boundary. The contrast can increase. It can also soften in subtle ways depending on how faint filaments evolve. The key idea is motion without obvious movement. Growth happens through gentle flow. The flow is measured in epochs, not moments. A slow, visual anchor forms as a wide cross-section of the void appears like a bowl. The center is shallow. The sides rise toward the rim. Along the sides, thin sheets of gas slide outward. The sheets are translucent. Their edges are smooth. Where sheets meet the wall, they fold into layered bands. Those bands look like overlapping veils pressed into a ring. The physical detail is the layering itself. It is not random. It reflects steady drainage. Dark energy is a component that causes accelerated expansion, like a background stretching of space that becomes more important over time, like a slow widening of gaps in a net even when the knots remain. It matters because it changes how quickly distant regions can influence each other. Growth factor is the measure of how density contrasts increase with time, like how a small dimple in clay deepens as the clay is pressed repeatedly, like how a faint track in snow becomes clearer after many footsteps. It matters because it predicts whether voids deepen or stabilize. A small payoff settles with these terms. Expansion can make voids appear larger and emptier in relative terms even without adding new emptiness. The interior density can drop relative to the cosmic mean because the mean changes and because matter keeps draining. Yet there is a competing effect. When expansion accelerates long-range, gravitational growth slows. Filaments stop strengthening as efficiently. New structure formation in low-density regions becomes less likely. This can freeze the void's internal texture. If the interior has a faint mesh, it may remain faint rather than becoming richer. If the interior is smooth, it may remain smooth. Another slow visual anchor shifts to the rim as time advances. The rim becomes slightly sharper. Its inner edge steepens. Its outer edge spreads into connected filaments. The rim looks like a shoreline where sediment accumulates. The shoreline does not move quickly. It thickens. It becomes more layered. Within those layers, gas cools and joins denser strands. The strands form a braided pattern. Each braid is a physical structure. It has a core and a sheath. The sheath fades outward with a gradient. That unlocks another point. The future of a void is not an empty waiting room. It is a slow sorting machine. Matter is sorted outward. Emptiness is sorted inward. The scale shift remains gentle. Inside the rim, gas clouds can change in millions of years. Along the rim, filaments evolve over billions of years. Across the whole void, the large-scale contrast evolves over the age of the universe. Each scale has its own tempo. A small payoff arrives. Slow does not mean static. It means the change is distributed across scales and time. A calm number can anchor the time axis. Over the next 10 billion years, accelerated expansion becomes more dominant, like a quiet increase in the spacing between fence posts on a long road. The comparison is imperfect. Fence posts are fixed. Cosmic structures are not. Yet the idea holds. Separation grows. Influence weakens. Filaments become more isolated from each other. Voids become more isolated as well. Another slow scene settles on the void interior. A faint gas sheet remains. It does not collapse into a rich filament. It stretches. It thins. It becomes harder to trace. The sheet's edges blur. The sheet's thickness becomes more uniform. This suggests that interior features can fade relative to the rim. That resolves a quiet question. A void that contains a faint skeleton today may contain an even fainter skeleton. Later, not because the skeleton vanishes, but because it stops growing, the limit of observation enters softly. Predicting the future relies on models that assume a background expansion history and a composition of the universe. Small uncertainties in those assumptions can change long-term outcomes. Another limit comes from the definition of void boundaries. As expansion stretches distances, the same physical region can be described with different coordinates. A void can appear to grow even if its comoving size stays similar. The limit is conceptual. Growth in one coordinate system is not the same as growth in another. This matters because intuition mixes size with emptiness. A void can grow in apparent diameter while its relative deficit stays nearly constant. Another small payoff settles here. The future of a void can be described in two languages, and confusion arises when those languages are mixed. A new everyday analogy arrives and stays unique. The void's future resembles a thin ink wash on paper that dries while the paper slowly stretches. The wash does not gain new ink. It spreads slightly. Its faint regions become fainter relative to the darker edge where ink pooled. The border becomes more pronounced. The interior becomes more uniform. The analogy is calm. Paper stretches in a simple way. Space expansion has a richer meaning. The shared idea is contrast changing under stretching. Another slow visual anchor returns to the rim where layers stack. The layers can form a shell-like structure. The shell is not a hard wall. It is a thickened band. Its inner face is steep. Its outer face is braided into the web. Within the band, gas density gradients become sharper. Those gradients can make absorption patterns more pronounced. They can also enhance faint radio glow if particles are present. That links back to earlier tracers. The future rim becomes easier to see in multiple ways. The interior becomes harder to see. Another payoff arrives. The strongest evidence of a void's existence shifts increasingly toward its boundary signatures. Now the story widens gently toward perspective. If accelerated expansion isolates regions, then voids become more separate cosmic neighborhoods. Each neighborhood carries its own history of initial fluctuations and drainage. The Boötes Basin becomes a case study in how an initial quiet patch can echo forward. It also becomes a reminder that large emptiness is not a gap in physics. It is a consequence of time and geometry. The next step is to step back again and consider how such voids influence other large-scale observables. The next step is to examine whether an extreme void can leave subtle imprints on background radiation patterns, and whether those imprints are consistent with a simple statistical tale. A void can leave a mark on light that never touches its rim. In that region, the Boötes Basin can be tested against an ancient glow that fills all directions. That glow carries tiny temperature differences. It also carries faint distortions in its texture. A large, under-dense region can nudge both. The nudge is subtle. It is a slower counting of gravity along a long path. A visual anchor appears as a dim spherical shell of microwave light. The shell is softly mottled. The mottling is gentle like faint cloud shadows on a calm surface. One patch looks slightly smoother. Another patch looks slightly cooler. Around it the mottling seems to lean. The lean is not a line. It is a weak preference in orientation. That preference is where the void can whisper. The integrated Sachs-Wolf effect is a late-time energy shift in passing light. Light behaves as a traveller crossing hills that slowly change while crossed, like a swell on a sea that rises while a wave passes over it, like a valley whose depth eases while a drifting shadow moves through. It matters because changing gravitational wells can imprint temperature changes on ancient radiation. The cosmic microwave background is relic light from an early hot universe, like a cooling ember field seen from far away, like a thin afterglow that remains when a bright flash is long gone. It matters because it offers a uniform screen behind later structures. A small payoff settles into place. A void can create a cold imprint on that screen not by blocking light, but by changing how gravity evolves. In an accelerating universe, large potentials can decay. A photon entering a potential and leaving it later can gain and lose unequal amounts. For an underdense region, the sign can become a mild cooling. The physical detail is a broad, soft gradient in temperature. It has no sharp edge. It looks like a shallow bowl in the mottled glow. The rim of the void can also influence the pattern. It can add a faint ring of opposite sign. The ring is not bright. It is a slight change in average temperature across a wide arc. Another visual anchor forms as that bowl is viewed in cross-section. The temperature gradient is smooth. It deepens toward the center. It relaxes outward. The transition is slow like dusk light fading across a plane. That calm shape unlocks another point. If the imprint exists, it should be wide and gentle. It should align with the void's projected position. It should not look like a small spot. It should look like a low-contrast basin spread across a large angle. A scale shift settles in. The microwave glow comes from about 13 billion years ago, like an echo that has travelled longer than any river can flow. The void is young by comparison. Yet the void can still affect that ancient light during its final stretch. In that region, light crosses the void long after it leaves the early shell. The crossing time is small compared to cosmic history. Still, the accumulated effect can be measurable in averages. A small payoff arrives. The void does not need to be ancient to write on ancient light. It needs only to lie along the path when the universe's expansion changes the rules of growth. Another visual anchor shifts from temperature to texture. The mottled glow also shows a faint pattern of bending. Its small features are slightly displaced. This is cosmic microwave background lensing. It is not a bright arc. It is a minute remapping of where mottles appear. Gravitational lensing is the bending of light by mass, like a ripple in air that shifts the apparent position of a distant ridge, like a clear stream that makes stones appear offset beneath the surface. It matters because it maps mass without relying on emitted light. A void acts like a negative lens. It defocuses slightly. It stretches features outward from its center. The physical detail is a subtle radial pattern in the lensing deflection field. The center shows a small divergence. The rim shows a change in sign. This pattern can be searched statistically. It is a second channel of evidence. Another payoff settles. If temperature imprint is weak or ambiguous, lensing can still show the deficit because lensing depends on mass directly. Yet limits arrive softly and clearly. The first limit is cosmic variance. The microwave sky has its own random large-scale mottles. A single void can sit atop a random warm or cool patch. That coincidence can mimic an imprint or hide it. The second limit is projection. Many structures along the line of sight contribute to lensing. A foreground ridge can cancel a void signal. A background cluster can add noise. The third limit is resolution. Large-angle temperature patterns are hard to separate from other large-angle modes. The limit is not only measurement, it is also the finite number of independent patches on the sky at that scale. Another visual anchor forms as many simulated skies drift by. Each sky has mottling. Each sky has different broad patches. A void is inserted into each. In some skies, the void appears as a clear, cool basin. In others, it blends into existing mottles. The variation is quiet but decisive. That scene unlocks another point. A single alignment can never prove a void is unusual. It can only shift probabilities. The evidence strengthens when many voids are stacked. When many similar basins are averaged, random mottles cancel. A persistent imprint can remain. The method is gentle. It's a search for coherence across samples. A new everyday analogy arrives and stays unique. The process resembles reading tide lines on a shoreline after many calm days. One tide line can be blurred by wind and debris. Many tide lines across many coves reveal a consistent height. The shoreline is natural, the tide line is subtle. The repeated pattern makes it real. In the same way, many voids can reveal a consistent microwave imprint. The Boötes basin can be compared against that ensemble expectation. Another payoff settles. If the Boötes imprint is far stronger than the ensemble, then the basin becomes more than a tale. If it is similar, then it becomes a rare but ordinary member of a known population. Another visual anchor returns to the rim. The rim is seen not as a wall of galaxies, but as a boundary and potential. Its gradient is where lensing changes fastest. In lensing maps, this can appear as a faint ring of enhanced convergence around an underdense center. The ring is broad, it is uneven. It follows the wall's thickness variations. That ring is a physical signature of the rim's layered mass. It connects earlier sections. Gas sheets, magnetic alignment, and shear patterns all point to the same boundary. The microwave imprint becomes another layer of the same story. Another payoff arrives. Multiple traces can converge on a single shape. Agreement across different physics is more persuasive than any single channel. Yet the story remains calm. Even perfect agreement would not require something exotic. It would only show that a large void behaves as gravity predicts under an accelerating expansion. The remaining tension would be rarity. How often does a void this large appear? How clean is its interior compared to typical basins? The limit of intuition appears softly again. Human expectation often underestimates extremes in large fields. A long tail can feel impossible until sample size is remembered. The microwave sky itself reminds this lesson. It is filled with rare alignments that occur somewhere simply because the sky is wide. The same principle holds for large-scale structure. Another gentle scale shift closes the circle. A tiny temperature difference on an ancient shell can reflect the shape of a vast hollow in the modern web. The link spans almost all cosmic time. It does so without any direct contact. It is only gravity and light in expansion. The next step is to let the account settle. The next step is to gather all the quiet signatures into a single calm picture and to ease toward a stable ending. A large emptiness can feel like a hole in understanding, yet it can also be a quiet confirmation of how the cosmos organizes itself. In that region, the Boötes void reads as a natural basin, in the cosmic web extreme in size but legible in shape and consequence. The rim carries the strongest signal, the interior carries the silence. Between them lies a gradient that matches slow gravitational drainage. The story resolves by holding these pieces together without forcing them into a single dramatic cause. A slow visual anchor forms as the void is imagined from very far away. The cosmic web appears like a faint lace draped across darkness. Filaments form long threads, nodes form denser knots. The void is a clear opening in the lace. Its boundary is a thickened ring. The ring is not perfectly circular. It undulates. It has thicker segments and thinner segments. Along the inner edge, the brightness gradient drops smoothly into the hollow. Along the outer edge, the ring blends into the wider web. The physical detail is this double-sided slope. It is the signature of a boundary that is both wall and connection. One concept settles first and stays simple. Under density is a region with less matter than average. Like a shallow basin on a landscape where rain runs away rather than pooling. Like a quiet patch in a crowd where paths avoid the centre and curve around. It matters because matter flow responds to differences, not to absolute emptiness. A small payoff arrives. The void does not need a special repulsive force inside it. Ordinary gravity can evacuate a region if the initial field gives it a head start. A second concept stays close. Shear is a pattern of stretching that distorts shapes, like pulling taffy so that one direction lengthens while another thins, like sliding layers of fog past each other so their edges become streaks. It matters because shear can align filaments and sharpen walls. The rim can be understood as a place where shear and drainage cooperate. Material drifts outward. The rim collects. Filaments become braided, layers form, gradients steepen, the interior becomes smoother. The pattern is slow, it is also persistent. Another slow visual anchor moves closer to the rim. A band of faint gas lies along the wall. Its thickness changes gradually. In some stretches it looks like a stack of translucent sheets. In others it looks like a single broad veil. In a few places the veil folds into a narrow ridge. The ridge casts a faint shadow in absorption against distant glow. No tools are shown, only the idea of light passing through a layered boundary. That scene unlocks a calm conclusion. The most reliable evidence of a void is often written in its edges. An emptiness is hard to measure directly. A boundary is easier. A boundary has gradients. Gradients shape light in predictable ways. A quiet number can anchor the scale without sharpness. A diameter of about 300 million light-years is wide, like spanning the length of a continent many times over. The comparison is only for scale. The real feeling is the smoothness of that span. Across that width, the interior remains underfilled. Across that width, the rim remains the organizer. The scale shift remains gentle. The rim's thickness can be described in millions of light-years. The growth of the basin happens over billions of years. The light that can carry an imprint comes from nearly the full age of the universe. Small things grow into large shapes. Large shapes leave small imprints. Another small payoff settles. The cosmos is a machine that trades magnitude across domains. It turns tiny early differences into vast geometry. It turns vast geometry into tiny shifts in light. The limit of observation is acknowledged softly and clearly. Any single void is difficult to define. Boundaries depend on traces. Traces can be sparse. Projection can hide structure. Algorithms can merge basins or split them. The limit is definition and sampling. Another limit is that the most subtle signals are close to the noise floor of cosmic variance. The sky itself provides only a few independent large-scale patterns. This makes certainty hard. Yet this uncertainty does not weaken the core picture. It clarifies what can and cannot be claimed. A small payoff arrives. A void can be real and well-formed even when its exact edge is a matter of convention. A new everyday analogy arrives and stays unique. The void resembles a wide, calm eddy in a slow river. The water inside the eddy moves. It moves gently. Leaves drift outward and gather along the rim where currents meet. The centre looks empty compared to the river's main flow. The rim is where motion becomes visible. The analogy is soft. A river is small. A void is vast. The shared idea is drainage and collection without a sudden event. Another slow visual anchor returns to the overall arc. The earlier clues align. The rim's layers match drainage. The interior's smoothness matches slowed growth. The probability tail matches the existence of rare basins in large volumes. The microwave imprint, if present, matches the expectation of a gentle temperature bowl and a weak defocusing lensing pattern. None of these require a new actor. They require patience and scale. The story resolves into a single calm statement. The Boötes void is not a thing hiding in space. It is a shape that emerges when the cosmic web is allowed to stretch and sort for a very long time. The remaining question is not whether it can exist. The remaining question is how often such a clean and large basin appears under familiar conditions. That question can be carried without urgency. It lives in statistics and surveys and slow refinement. The final scale shift eases toward rest. The void is a quiet region in a vast structure. The vast structure is a quiet perturbation in an even larger expansion. In that region, light continues to travel. Gradients continue to soften and sharpen in slow balance. The rim remains a calm boundary. The interior remains a calm silence. The next moment is simply the next moment. The darkness holds its shapes gently.